Welcome to a primer on prediction. We'll be reasoning together throughout this course about quite challenging theoretical and empirical problems. To help us in doing this better, I'm going to introduce a few key ideas and techniques for clearer thinking and more accurate prediction. This primer will consist in 3 parts. First, thinking in probabilities. Second, thinking like a forecaster. And third, correcting for biases. Let's begin with 3 examples to motivate the project of good prediction. First, up until the early to mid-20th century, before the invention of vaccination and later adoption of evidence-based medicine, it is estimated that visiting a doctor lowered one's life expectancy. I want you to imagine all of the doctors throughout history, from all of the different medical traditions around the globe. I would posit that a large fraction of them were very well-intentioned indeed. If any of you know doctors, many of them are truly very decent people. And the last thing they would want to do is to lower the life expectancy of their patients. However, to see why it is that this was often true, you need only think through what it means that almost every medical tradition has developed a practice of surgery. So all of the different cultures at one time or another stumbled upon the idea that cutting a human open may be good for their health. However, in the absence of a germ theory of disease and an understanding of the importance of sanitizing every surface in a theater of operation in order to prevent infection, every one of those expeditions into surgery were almost sure to do more harm than good. In this way, we see how humans, even with the best intentions, can live in profound misunderstanding of the impacts of our actions and the character of our world. And that it can matter because it can confound our deepest aims and desires. Second, the year-to-year correlation between the outcomes of mutual funds is very small, barely higher than 0. There is general agreement among researchers that nearly all stock pickers, whether they know it or not, and few of them do, are playing a game of chance. From Kahneman, Thinking Fast and Slow. Mutual funds are run by highly experienced and hardworking professionals who buy and sell stocks to achieve the best possible result for their clients. Nevertheless, the evidence from more than 50 years of research is conclusive. For a large majority of fund managers, the selection of stocks is more like rolling dice than like playing poker. At least 2 out of every 3 mutual funds underperform the overall market in any given year. Kahneman, don't blink, the hazards of confidence. To be sure, at any given time, there are plenty of managers who have recently beaten the market smartly. And if you look around, you'll even find a few with records that have been terrific over 10 years or more. But just as a coin flipping contest between thousands of contestants would no doubt yield a few who had uncannily called it a dozen or more times in a row, the number of market-beating mutual fund managers is no greater than you would expect as a result of pure luck. Fama in French, luck versus skill in the cross-section of mutual fund returns. Third, studies tracked the accuracy of hundreds of experts for dozens of countries on topics as disparate as transitions to democracy and capitalism, economic growth, interstate violence, and nuclear proliferation. When we pit experts against minimalist performance benchmarks, dilettantes, dart-throwing chimps, and assorted extrapolation algorithms, we find few signs that expertise translates into greater ability to make either well-calibrated or discriminating forecasts. Tetlock, expert political judgment. Here we have a figure from Tetlock's expert political judgment. Across the x-axis, we have calibration, and across the y-axis, we have discrimination. So that higher values in both are good, and being in the upper right indicates the best forecasts, the lower left, the worst forecasts. In the lower right, one sees random algorithms as a benchmark. Throughout the rest of the image, we see in the lower left all of the pundits who are labeled by the clusters hedgehogs, hedgefoxes, and foxhogs. We will get into what these terms indicate. Suffice it to say that all of the pundits are in this central area of rather poor performance, comparable to random algorithms and mindless competition. Of course, undergrads have done an impressive job in the lower left of actually being anti-predictors. And simple formal models, these are things like linear regression, outperform the crowd. Perhaps we can add a fourth example and consider my own field of philosophy. Here, I can say that if one were to look at significant philosophers in the history of philosophy, take folks like Aristotle or Kant or Nietzsche, and if we asked them about their theories of metaphysics, their theories of the nature of space and time and so on, what is their prediction, their probability on any of these theories being true, their theories in particular? What you would find almost surely was a really immoderate overconfidence in those theories. And this would be of the sort that if they were thinking sufficiently clearly, I believe they should have, with the knowledge that they had at that time, been able to arrive at a better calibrated, much lower confidence on their own theories. They should have been able to notice how much disagreement existed among their peers. Think more deeply into the logical structure of how many distinct claims would have to be true for their theory to turn out to be right. Or even more deeply into how big a possibility space of true theories existed and how small a fraction of that their current theory carved out. Any of those lines of reasoning should have substantially decreased their confidence. And yet, I am hard-pressed to think of any philosophers in history who had this sort of appropriately moderated confidence. To list off just a few further examples, we've seen that simple statistical prediction rules have been used to predict the auction prices of Bordeaux better than expert wine tasters, marital happiness better than marriage counselors, academic performance better than admissions officers, criminal recidivism better than criminologists, and bankruptcy better than loan officers, to name just a few examples. For further reading, I recommend Tetlock's Expert Political Judgment, which presents a body of research on the conditions under which we should and should not trust expert judgment. All this has been to motivate the assertion that we can and should do better. It is possible to overcome biases, to calibrate our confidence, and to increase our accuracy, even in predicting complex real-world phenomena. As an example, as a part of the Good Judgment Project, a group of amateur forecasters outperformed U.S. intelligence analysts every year for several years going. As a part of an IARPA-funded competition, Tetlock and colleagues recruited amateur forecasters and gave them a bit of debiasing training. This group performed substantially better than all the other competitors, and indeed the formal competition was cancelled after 2 years. When compared to the aggregate of predictions from the U.S. intelligence community, these amateur forecasters did substantially better. And note that they did so without access to classified information. The Good Judgment Open is the legacy of this project, an ongoing public forecasting tournament for all. And we will be using many of the insights produced by the Good Judgment Open, as well as the larger body of research from Tetlock and colleagues, to think through the conditions for better prediction. thinking in probabilities. The dominant framework for conceptualizing the attitude of belief in philosophy is known as full belief. For example, the concept of knowledge is often assumed to consist of justified full belief, and perhaps a further condition, when one either has a belief in a proposition or one does not. We will be reasoning about complex empirical phenomena, about which we should have varying degrees of uncertainty. The all-or-nothing epistemic attitude involved in full belief is ill-suited and inadequate for our purposes. We will be reasoning about complex empirical phenomena, about which we should have varying degrees of uncertainty. The all-or-nothing epistemic attitudes involved in full belief are ill-suited and inadequate for our purposes. Indeed, full belief is beset by various paradoxes. Consider the following. A scholar has written a book. Within its pages, they have made hundreds of claims. They can reasonably believe each of these claims. They can also reasonably believe that at least one of these claims is false. Representing this formally, let BHI denote that the author believes the claim HI, and denote the claims in the book by propositions H1 through HN. Then we have that the author believes each claim in the book, BH1 through BHN. It follows that they believe the conjunction of these claims. the author believes that at least one of the claims is likely false. So they believe the disjunction of the negation of these claims. By De Morgan's law, this is equivalent to the following: that they believe the negation of the conjunction of these claims, from which it immediately follows that they do not believe the conjunction of this claim. Contradiction. This apparent paradox is resolved by moving to a probabilistic framework for belief. The author can now have a high probability that each claim in the book is true. For example, let the probability of the truth of each claim, 1 through n, be equal, at some value alpha greater than 1/2. And the author can believe that at least one claim is likely false. For simplicity, assume the claims are probabilistically independent. Then we have the probability of there being at least one false claim is the probability of the disjunction of the negations of the claims, which is equal to the probability of the negation of the conjunction of the claims by De Morgan's law, which is equal to 1 minus the probability of the conjunction of the claims by the negation rule, which is equal to 1 minus the product of the probabilities of the various claims by independence, which is equal to 1 minus alpha to the n, which can reasonably be very high. For example, let the author have a subjective probability of 0.95 in each of the 100 claims. This yields 1 minus 0.95 to the 100, which is approximately 99.4% that at least one of the claims is false. So what does a probabilistic framework for belief consist in? This is often taken to have two parts: the theses of probabilism and conditioning. Probabilism states that our beliefs should conform to the probability axioms. And conditioning states that we should change our beliefs in light of new evidence via Bayes' rule. Specifically, that our new credence upon the event of learning some evidence E in hypothesis H should be our old conditional credence in the hypothesis E given evidence E. Some useful propositions from the probability calculus include normality, that the probability of any event is between 0 and 1. Negation rule, that the probability of the negation of an event is equal to 1 minus the probability of that event. The implication rule, if an event implies another, that entails that the probability of the first is at most as great as the second. The disjunction rule, that the probability of the disjunction of two events is equal to the sum of their probabilities minus the probability of their intersection or conjunction. Two concepts worth remembering are those of mutual exclusivity and independence. Two events are mutually exclusive if their conjunction is equivalent to the contradiction. If two events are mutually exclusive, then the probability of their conjunction is equal to 0. For example, a coin coming up heads and tails, or a die coming up 1 and 6. Are mutually exclusive events or propositions. Two events are independent if the probability of their conjunction is equal to the product of their probabilities. Equivalently, A and B are independent if the probability of A conditional on B is equal just to the probability of A. Note that mutually exclusive events are not typically independent. Indeed, they are highly dependent. Think of the difference between a coin coming up heads and tails, as in the case of mutually exclusive events, versus two coin flips, the first coming up heads and the second coming up tails. In the latter case, this is an example of probabilistic independence. For example, if A and not A are mutually exclusive, then the probability of A given not A is equal to 0, which is not equal to the probability of A, meaning that it is clearly not independent. If, of course, the probability of A is greater than 0. An intuition here is that learning A is not true changes the probability that it is true. And in general, two propositions can be thought of as probabilistically independent if learning one gives us no predictive information for the value of the other. Conditional probability can be defined as follows. The probability of A given B is equal to the ratio of the probability of the conjunction of A and B over the marginal probability of B. We can visualize probabilistic statements in terms of areas. Here, the probability of an event is equal to the area of the event over the area of the sample space. Similarly, we can see that the probability of A given B is equal to the area of A and B over the area of B. How to think about Bayes' rule? On one hand, it is simply a theorem of the probability calculus. On the other hand, it has a place as a principle for rational learning on many accounts. What Bayes' rule teaches us is how precisely to combine our old beliefs with evidence to produce new beliefs. We can derive Bayes' rule with just a few steps, beginning with the definition of conditional probability from before. By multiplying both sides of the equality by the probability of B, we get the following expression. Using that expression, we have that the probability of A and B can be written as the probability of A given B times the probability of B. By symmetry, the probability of A and B can also be written as the probability of B given A times the probability of A, making those two formulations equivalent. Now we have that the probability of A conditional on B times the probability of B is equal to the probability of B given A times the probability of A. Finally, we divide both sides of the equality by the probability of B. This is Bayes' rule. A and B are merely propositions. There's no fundamental difference between them. However, in learning situations, we're often interested in the probability of one proposition, a hypothesis of interest, given the truth of another proposition, a recently learned piece of evidence. This gives us a familiar formulation of Bayes' rule. The odds formulation of Bayes' rule is particularly useful for quick mental calculation. What it tells us is that the posterior odds of hypotheses H and not H, conditional on some evidence, is equal to the product of the prior odds on the hypotheses and the likelihood ratio of the evidence given each hypothesis. This also clearly identifies for us a key measure of what evidence is, namely the likelihood ratio. Our initial beliefs are captured by the prior odds. Our beliefs after learning are captured by the posterior odds. And what it is that we are learning is fully specified by the likelihood ratio. The content of any piece of evidence is simply equal to the ratio of its likelihood under the relevant hypotheses. This tells us a few deep and interesting things. First, that evidence is relational. It matters critically what it is in terms of hypotheses and the likelihoods of that evidence given by their ratio. There is no impact of evidence without a comparison between its impact on various hypotheses. Further, it indicates to us that in most situations, everything is at least weak evidence for everything else. Only in the cases where two propositions or events are completely probabilistically independent of one another, right, or induce identical likelihoods of the evidence, do we get that the evidence or an event does not serve to change our probabilities about those hypotheses. In this way, the odds formulation of Bayes' rule elucidates the character of evidence. Using Bayes' rule to update one's beliefs has a property worth knowing, namely that upon updating one's beliefs and arriving at a posterior probability, that posterior probability will provide the prior probability for one's next update on receiving yet another piece of evidence. One can remember this with the statement, today's posterior is tomorrow's prior. This process can be repeated indefinitely. There are theoretical arguments that Bayes' rule may not just be another way to learn, but may actually describe the uniquely rational way to learn. The arguments marshaled in favor of this conclusion are known as accuracy dominance arguments, Dutch book arguments, representation theorems, and syntactic consistency arguments. There are theoretical arguments for why Bayes' rule may not just be another way to learn, but may actually describe the uniquely rational way to learn. These are synchronic and diachronic accuracy dominance arguments, which state that if one's beliefs do not conform to the probability calculus, and one does not update one's belief via Bayes' rule, then the nearest probabilistic reasoner to oneself will do at least as well in prediction as scored by any proper scoring rule in all worlds, and strictly better in some. That is to say, there is a probabilistic reasoner that will dominate one in accuracy. Dutch book arguments, which state roughly that if one's beliefs do not conform to the probability calculus, and one does not update one's beliefs via Bayes' rule, then one is open to a sequence of bets that commits one to a sure loss. And conversely, if one's beliefs are probabilities and one does update via Bayes' rule, then one is not vulnerable to any such sure loss. Representation theorem arguments state roughly that beginning at a rational representation of one's preferences or choice behavior, that is to say, behavior that satisfies basic condition, like transitivity, that if one prefers A to B and B to C, then one prefers A to C, that building on this basis, one can come to represent an agent after several steps as having beliefs that conform to the probability axioms and updating those beliefs via Bayes' rule again. And if one cannot represent an agent as doing that, then one must violate one of these basic assumptions of rationality, like transitivity. Finally, syntactic consistency arguments state something like, if one's beliefs are not conforming to the probability calculus and one does not update via conditioning, something to the following effect is true, that one assigns probabilities to various propositions that are logically equivalent, that are probabilistically distinct. So imagine the propositions A and B and A. These are logically equivalent, but syntactically distinct. If one is not abiding by probabilism and conditioning, then somewhere in one's algebra of beliefs, then there is this sort of inconsistency at play. We'll not go deeper into these theoretical justifications for probabilism and conditioning here. Suffice it to say, you can look more deeply into the theoretical debates in this issue. One more result from probabilistic reasoning that is worth noting in passing is Bayesian convergence theorems, often given by what are known as martingale convergence theorems. These show that if an agent's beliefs are probabilities, and that she assigns positive probability to the true hypothesis, then given sufficient evidence, in the limit, she will converge to applying probability 1 on the true hypothesis. These are sometimes used to reassure those who worry about the introduction of a kind of inherent subjectivity in the form of prior probabilities in Bayesian learning. The worry there goes something like, we start with these initial guesses that seem to be ultimately judgment calls. But if probabilistic learning is supposed to work as a foundation for science, we are undermining the objectivity of science by acknowledging this inherent element of judgment. Bayesian convergence theorems are meant to reassure this worry by showing that even if we begin with different initial judgments, as we learn more and more, those priors will wash out of our later estimates, and the data will come to dominate our posterior probabilities. All that said, like many frameworks, Bayesian inference has its limitations. Here are a few. The problem of old evidence observes that Bayesian agents are closed under deduction with respect to their algebras. This means that they know the logical relationships between the propositions they entertain. However, we as people do not. That is to say, we could know a theory and a piece of evidence without being aware that one logically implies the other. And we can come to learn this. One can think of historical episodes where a scientist had a theory that they were developing and suddenly had the epiphany that some already known piece of evidence was implied by that theory, thereby lending it support. In the Bayesian framework, this does not make sense. And so one piece of kind of natural bounded reasoning that humans do is not able to be captured effectively in this framework. Similarly, there is no elegant, optimal solution for how to add new hypotheses to the set of hypotheses we consider. We often will want to do this because there are hypotheses that we will discover but that we did not initially have anywhere in mind. Well, when we're doing probabilistic reasoning, we can add them in and renormalize our probabilities, but there is no answer about how to do this optimally coming out of the probability calculus. In general, the framework of probabilistic reasoning assumes deductive closure, and that makes it particularly hard to think about how does one learn logical relationships. A fundamental and pragmatically quite important limitation of Bayesian learning is computational tractability. When one wants to spell out more complex models of the world, one needs to consider many, many different propositions and their relationships. One needs to think about our uncertainty about our uncertainty about our uncertainty, and this structure is often impractical to work with. So even if we know that for any inference problem there is some optimal agent that is a Bayesian agent who could be dealing with this problem, we will often have to resort to more bounded and heuristic methods. And you can think of much of statistics and machine learning as finding such bounded but practicable methods. Some further reading here. I recommend Jeffrey's Subjective Probability, The Real Thing, Jane's Probability Theory, The Logic of Science, and particularly the two books of Tittlebaum's Bayesian Epistemology. This is all interesting, but let's discuss how concretely to use probabilities in practice. To do probabilistic reasoning, we often need to begin with estimates of our uncertainty about various propositions. One way to elicit your subjective probabilities is to bet on it. At what odds would you be willing to bet on a proposition? For example, suppose someone offers you a bet at even odds that Biden will be re-elected. Would you take it? What about 2 to 1 odds? 10 to 1? In theory, the knowledge that money is at stake should motivate you to get at the truth of the problem and maximize your chances of winning. That is, to give yourself skin in the game. A drawback of this method is that it only works when utility is linear with respect to money, and you are not risk averse. In the simplest case, I should be indifferent to a $100,000 bet at 50% odds that a fair coin will come up tails. But in fact, I would refuse it. Winning $100,000 would be moderately good, but losing $100,000 would keep me deeply in debt and is generally not worth it. Another way to elicit your probabilities is to convert to a frequency. How many situations would it take before you expected an event to occur? For example, you need to give a probability that the sun will rise tomorrow. $999,999 in a million doesn't immediately sound wrong. The sun seems likely to rise, and a million is a very high number. But if tomorrow is an average day, then your probability will be linked to the number of days it will take before you expect that the sun will fail to rise on at least one. A million days is 3,000 years. The Earth has existed for far more than 3,000 years without the sun failing to rise. Therefore, 999,999 in a million is far too low a probability for this occurrence. If you think the sort of astronomical event that might prevent the sun from rising happens only once every several billion years, then you might consider a probability more like 999,999,999,999 in a trillion. This method fails if your case is not a typical one. And so looking at past frequencies is not appropriately informative. For example, if your city is on the losing side of a war against an enemy known to use firebombing, the probability of a fire at your city has little to do with the average frequency of fires across cities. Or, for example, if you think the reason the sun might not rise is a supervillain building a high-tech sun-destroying machine, then consistent sunrises over the past 3,000 years of low technology will provide little consolation. Our third and final way to elicit your probability estimates is to find a reference class. How often have similar statements been true in the past? For example, what is the probability that the latest crisis in Korea escalates to a full-blown war? If there have been 20 crisis-level standoffs in the Korean Peninsula in the past 60 years, and only one of them has resulted in a major war, then war conditional on crisis is equal to 0.05, or 1 in 20, so long as this crisis is equivalent to the 20 crises you are using in your reference class. But finding the reference class is itself often a difficult problem. What is the probability that Bigfoot exists? If one makes a reference class by saying that the Yeti doesn't exist, the Loch Ness Monster doesn't exist, and so on, then the Bigfoot partisan might accuse you of assuming the conclusion. After all, the likelihood of these creatures existing is probably similar to and correlated with Bigfoot. The partisan might suggest asking how many creatures previously believed not to exist later turned out to exist, a list which includes real animals like the orangutan and platypus. But then one will have to debate whether to include creatures like dragons, orcs, and Pokemon on the list. Finding a reference class works best when the reference class is more obvious, as in the Korea example. Otherwise, you may find yourself stuck in an unproductive game of reference class tennis. We'll see this challenge in the context of AI safety research, as key events to be forecast, for example, the timelines and capabilities of novel artificial superintelligences, have never occurred before. Thinking like a forecaster. In the previous section, we saw that in the work of Tetlock and colleagues on expert political judgment, pundits in general did not perform particularly well when held accountable to making clear and falsifiable forecasts. That said, insofar as there was variation between the quality and competence of forecasts, there were broadly two clusters of traits that best identified better and worse forecasting ability. These clusters of traits have come to be named fox and hedgehog-like traits. The names originate from a fable by Rudyard Kipling, in which the fox knew many small things and the hedgehog knew just one very big thing. In particular, the traits captured by the archetype of the fox are the belief that the world is complicated, that many perspectives are better than a single perspective, and the disposition to being more humble and less confident about one's understanding of the world. These predicted better forecasting. The traits associated with the hedgehog are that the world is simple. Think that everything could be understood in terms of class struggle or ethnic conflict. One theory explains everything. And dispositionally, hedgehogs tend to be much more confident of their understanding of the world. Insofar as we're able to emulate these traits, the recommendation then is to appreciate the complexity of the world, to draw from many perspectives, and to be more humble about our understandings. One standard measure of accuracy in forecasting is the Breyer score, which is given by the following formula. Intuitively, one can think of this as the mean squared error of one's predictions. In binary prediction tasks, the Breyer score will range between 0 and 1, where 0 is perfect accuracy. That is, there is no error in the forecast, and 1 is perfect anti-prediction. That is, a performance such that if one were to bet against your predictions, they would do perfectly well. If one is guessing at chance in the binary prediction task, then one's expected Breyer score is going to be 0.25, because one's average inaccuracy is going to be 0.5, and 0.5 squared yields 0.25. The way to unpack the formula is to observe that we have n prediction items, so that we are taking the mean, 1 over n, for the accuracy over those items. For each item, t, the outcome is denoted by O sub t, which takes the value of 1 if the outcome occurs, and 0 if the outcome does not occur. F of t is the forecaster's probability judgment. One observes the difference, the error, squares the error, and then takes one's average over all prediction items. Suppose that one is forecasting the probability F that it will rain on a given day. Then the Breyer score is calculated as follows. If the forecast is 100%, F is equal to 1, and it rains, then the Breyer score is 0, the best score achievable. If the forecast is 100% again, but it does not rain, then the Breyer score is 1, the worst score achievable. If the forecast is 70% and it rains, then the Breyer score is 0.7 minus 1 squared, or 0.09. In contrast, if the forecast is 70% and it does not rain, then the Breyer score is going to be 0.7 minus 0 squared, or 0.49. Similarly, if the forecast is 30% and it rains, then the Breyer score is 0.49. And if the forecast is 50%, then if it rains or does not rain, the Breyer score will be 0.25, regardless. We can understand what accuracy consists in by decomposing it into three elements: calibration, resolution, and uncertainty. More granularly, one's inaccuracy in terms of the Breyer score can be thought of as the sum of the three terms. One, the difference between one's forecast probabilities and the objective base rates of events given by the calibration, minus the difference between the objective base rates of events and one's conditional forecasts given by the resolution, plus the inherent variance in the outcomes of events. Let's take this term by term and spell it out carefully. Intuitively, calibration measures how far one's forecast probabilities are from the objective base rates of events. The lower, the better here. Note that this is the opposite of one use of calibration in everyday language. Here, less calibration is better rather than more. For example, for events where their forecasted probability is 90%, we would want 90% of them to be positive outcomes. For the 50% forecast, we would want 50% positive outcomes, and so on. We want our forecast probabilities to match those objective base rates. One can conceptualize what over and underconfidence means by examining calibration curves. If one is overconfident, then the average probabilities assigned are greater than the percent correct. Imagine one is applying an average of 90% to events that tend to come out only 70% of the time. In such a case, one is overconfident. One is well calibrated if one's average forecast corresponds to those objective base rate, to the percent correct for each category of forecast, if one were to bucket them. So, as we said, what is well calibrated if our 20% forecasts come true 20% of the time, our 40% forecasts come true 40% of the time, and so on. And of course, one is underconfident if our average forecast is lower than the objective base rate. So one is assigning something like 50% to outcomes that on average come out 90% of the time. This would be underconfidence. Visually, by examining the graph here, notice that the forecast probabilities are on the x-axis, and the objective base rate, or the percentage correct, is on the y-axis. Then, if one's empirically observed forecast or calibration curve is below the diagonal line, one is overconfident, because when forecasts exceed the objective base rates. If it's above the diagonal line, then one is being underconfident, and the diagonal represents the line of perfect calibration. Empirical studies of folks' confidence in general demonstrates that we tend to be stubbornly overconfident. These calibration curves are taken from normal folk given a series of wide-ranging prediction tasks from Lichtenstein et al., 1997, that said even forecasters who get quite good at forecasting move toward the line of perfect calibration from below. That is to say, good forecasters start overconfident, become better calibrated in their confidence, but often still maintain just a slight bias in the direction of overconfidence. This is the tendency for most people, and one to try to be aware of. These are some quite impressive calibration curves from the IARPA hybrid forecasting competition, where in blue we have the most calibrated forecasters given by the good judgment super forecasters. And the red line is given by the best performing competitors who are using a combination of algorithms and human forecasters in the hybrid case. Resolution intuitively measures how the conditional probabilities given the different forecasts differ from the base rates. Here, the higher the better. In the worst case, every forecast is exactly equal to the base rate. The resolution is 0. In the best case, all the forecasts are 1s and 0s, and the resolution is equal to the uncertainty. Another way to think of resolution is when one is correct or knows something about the item they're forecasting, how much are they able to differentiate their forecast from chance? Again, resolution can be thought of as capturing, when one does get their forecasts right, how confident were they in their predictions. Good resolution means that you were decisive, that when you got your prediction correct, you made it at a confidence, say, of between 70 and 90%, or 10 and 30%, resulting in large gains in your overall Breyer score. Bad resolution means that when you got your predictions right, you stuck to a timid band of 40 to 60%, meaning you never won big bumps in your overall Breyer score. Uncertainty measures the inherent variance in outcomes. Here, the lower the better. For example, if all outcomes are 1 or 0, that is to say they are the same, uncertainty is minimal and equal to 0. If precisely half the outcomes are 1, uncertainty is maximal and equal to 0.25. Note that this is the only term that does not depend on the forecaster's probabilities, and that this term is basically the variance of a Bernoulli trial. You can think of this as the portion of uncertainty that is bound intrinsically to the subject matter itself. Putting calibration and resolution together, we can look at these two examples. On the left, we have a case of good calibration, but low resolution. Here, notice that when it's calibrated, insofar as our 40% forecasts tend to occur at 40% of the time, and our 60% forecasts tend to occur 60% of the time. In this sense, these forecasts are well calibrated. However, notice that when they're on the right side of 50%, these are low confidence forecasts. In contrast, we can move to the right and consider well-calibrated and high-resolution forecasts. Now, when the forecaster is correct, their confidence is quite high, between 80 and 100%. The forecaster on the right maintains calibration but exhibits higher resolution, producing a greater Brier score, or rather a lower Brier score and a greater accuracy. Frequency prediction. On your laptop or with a peer, test your ability to estimate the frequency of events and compare your scores to other users. You can find this activity on the Clear Thinking website by searching Clear Thinking and calibrate your judgment. This should take around 30 minutes. When you have completed this, move on to the next activity. Calibration practice. On your laptops or with a peer, test and refine your calibration and compare your under or overconfidence to other users. You can find this on the Clear Thinking website by searching Clear Thinking and improve your frequency predictions. This activity should take 15 minutes. When you have completed it, feel free to move on. Correcting for biases. Here we define a bias as a pattern of reasoning that tends to lead to errors in belief or to lower accuracy in forecasts. A corrective is an action aimed at improving an error. Here, one meant to improve one accuracy in forecasts. The biasing training could address a huge range of different biases. Here we will focus on several biases that are particularly relevant for accuracy in prediction. We will look at motivated reasoning and confirmation bias, base rate neglect, availability heuristic, and the conjunction fallacy. For our first two biases, we will look at the availability heuristic and confirmation bias. To simplify, we can summarize their implication as follows. In general, as reasoners, we move far too quickly from confusion and uncertainty to confident conclusions without reflecting nearly enough. Here we will define the availability heuristic as a tendency to judge the likelihood of an event by how easily it comes to mind, how available it is to cognition. Note that with most biases, they will tend to have some sort of function. That is to say, there are some contexts in which they're reasonable heuristics. In particular, one will often find that they will line up with something we call ecological rationality. In our ancestral environments, many of the heuristics and biases we'll look at were quite adaptive when one had different learning contexts than those that we're exposed to today, or one wanted to find a good, satisfying solution under constraints of time, computation, and so on. However, it is important for us to identify the context under which those heuristics that might have worked well for certain purposes will tend to fail us. Let's consider some cases where the availability heuristic is likely at play. Things that are easy to recall are plane crashes, whereas safe flights are going to come to mind less intensely, which can lead to a fear of flying or an overestimation of the likelihood of plane crashes. Cold spells and extreme weather events will be easier to recall, whereas gradual changes in climate will be quite a bit harder to detect or bring to mind. This can lead to not appreciating the overall statistical trends in climate. Winning lottery tickets are quite a bit more memorable than ubiquitous losing lottery tickets, producing an exaggerated estimate of the likelihood of winning the lottery. Everyone knows, for example, with some reasonable probability, someone who has won something or has done well at the casino or some other low probability event. And if you were to scan your memory and put the number of times you recall someone doing kind of mediocrely in the context of lotteries or gambling or whatnot, next to the times that you recall someone doing quite well, you'll notice that that is nothing like the objective base rates of those two events. So what causes cognitive availability? The factors that tend to make something more available to our cognition are vividness. That is to say, events are more available when they're easily imagined and visually striking. Extremeness, more dramatic or extreme events are more available to memory. Events that produce negative emotion. The more negative emotion that's produced by contemplating a given event, the more easily it can typically be remembered. The frequency with which the event is encountered. Events that are encountered more frequently, either personally or through media, are more available. This is true, of course, even if the frequency with which the media reports an event is way out of line with its objective base rate of occurrence. Recall the activity you completed earlier on the Clear Thinking website, which had the pairs of causes of death whose relative frequency you had to estimate. The pairs were typically constructed so that each pair included a less common but more available cause that is vivid, extreme, negative, or frequently reported, and a second, more common in terms of objective base rate, but less available cause, mostly lacking or having less of these characteristics. Some examples. Accidental falls compose 5 times more deaths than war and terrorism. Asthma causes around 3 times more deaths than war and terrorism. Rheumatoid arthritis causes around 6 times more death than forces of nature. And accidental drowning causes around 3 times more deaths than opioid use. In sum, the availability heuristic functions to misrepresent the objective frequency of events to us, and consists in the tendency to overestimate the prevalence of events that are either recent, extreme, negative, or overly reported. So, how do we correct for this? The corrective here is to find or create rigorous probability estimates for events. Statistics and data are helpful here, but beware selection bias in both human cognition and in data collection. The corrective here is to find or create rigorous probability estimates for events. Data and statistical analysis are helpful here, but beware selection bias both in human cognition and in data collection. Our next bias is confirmation bias. There are many things that have gone by the name of confirmation bias. Here, we will focus on the following version. We will take confirmation bias to be the tendency to seek, interpret, or recall data in a way that confirms one's current favored hypothesis. This also sometimes goes by the name of motivated reasoning. Visually, we might think of confirmation bias as the selective noticing of the intersection of the facts with what would be confirming of our current favorite hypothesis. The deranging effects of confirmation bias have long been studied. Here we have Sir Francis Bacon in his Novum Organum observing, the human understanding, when it has once adopted an opinion, draws all things else to support and agree with it. And though there be a greater number and weight of instances to be found on the other side, yet these it either neglects or despises, or else by some distinction sets aside or rejects. So what is the corrective here? I will suggest 2 approaches. First, it is invaluable to spend time considering alternative hypotheses to flesh out the space of possible hypotheses. As an exercise, before settling on a hypothesis that you'll use as your explanation for one or another phenomenon, take 5 minutes during which you assume your hypothesis is false. Now list off as many alternative hypotheses as you can think of. I find that this will reliably change your probabilistic assessment of your first hypothesis. Putting it in a space after you've assumed it's false and considered many alternatives will typically indicate that you were initially seriously overconfident in your first guess. Next, look for disconfirming and not just confirming evidence. Our minds tend automatically to try to confirm what we believe. Therefore, given this disposition, it is crucial to find evidence that works against this sort of favoring behavior. That said, to get to a really clear thinking state, it is ideal to work in such a way that you don't actually favor hypotheses, but rather see a set of hypotheses and simply consider the way that the evidence will move your probabilities over the whole set. But until you find yourself in that ideally dispassionate place, correcting for the tendency to favor one another hypothesis is really quite important. For example, imagine that you are in seminar when a friend of yours gives you a look as though they may be upset. The first hypothesis that might come to mind was that that friend, let's call them Omid, was upset with you. Now, once that hypothesis has fallen into place, there can be the tendency to look for evidence that differentially supports it. However, that would be a mistake. Before looking for evidence for one hypothesis, let's spell out some alternative hypotheses to flesh out the space of possibility. Right. Notice that the complement of this hypothesis, its negation, is actually a disjunction of many other distinct possibilities. Perhaps Omid was having a bad day, and the look of upset did not have to do with me, but about some other part of their day. Perhaps Omid was not at all upset, but rather deep in thought, which was what the face was reflecting. Perhaps Omid had to pass gas and was in physical distress as a result. Perhaps he was feeling some other form of pain, which reflected itself on his face. What else? I want you to take a minute and consider alternative hypotheses. When you have done so, feel free to move on. If the hypotheses are actually exhaustive of the ways we could have received our evidence, E, then what we have is that E will be logically equivalent to the disjunction that E is true and hypothesis 1 is true, or E is true and hypothesis 2 is true, and so on, until we have completed enumerating our exhaustive set of hypotheses. Considering the probability of E then, we get that it is equal to the probability of the logical statement just mentioned, that E is true and hypothesis 1 is true, or E is true and hypothesis 2 is true, and so on. Assume for simplicity that we have done a sufficiently clean job of carving up our hypothesis space such that each of those is mutually exclusive. So Omid being deep in thought and Omid having a bad day are mutually exclusive. This yields that the probability of E, the face that Omid made for us, is equal to the sum of the probabilities of each of those disjoint propositions, that E is true and H1 is true, and so on. This is by additivity, which then, by the definition of conditional probability, can be unpacked into the sum of the probability of the likelihood of E given each hypothesis times the prior probability of each hypothesis. So the probability of E, the face that Omid made, given hypothesis 1, say that Omid was upset with you, times the prior probability that Omid was upset with you, plus the probability of the face that Omid made conditional on Omid was having a bad day, times the prior probability that Omid was having a bad day, and so on. The probability of our evidence that Omid made a face is now unpacked in a way that we can work with more easily. For simplicity, let's make it so that all of the likelihoods are equal. That is to say, the probability of the face that Omid made, conditional on each of our hypotheses, is about 1/2. We now need the prior probabilities for each of those underlying hypotheses, H1 through H4. So let's make some estimates. Perhaps 4 out of 100 times, or 1 out of 25 times equivalently, Omid is upset with me on a given day. So perhaps something like once a month, Omid gets upset with you. 80 out of 100 times, Omid is having a bad day. That is to say, maybe 8 out of 10 days, Omid's not having a great day. Perhaps it's a difficult period in Omid's life. Say 16 out of 100 times Omid was deep in thought. Omid is thoughtful from time to time. And 2 out of 100 times Omid had a heart and was in distress. Importantly, if these hypotheses are mutually exclusive, they should sum to 1. We can now plug these into Bayes' rule, where the probability of the hypothesis that Omid was upset with you, given that he made that face, is simply equal to the probability that Omid was upset with you and he gave you that face, unpacked in the familiar way, over the probability of all of the ways that Omid could have made that face, the probability of our evidence, unpacked in the way that we just did, by the law of total probability. Since we stipulated that all hypotheses make the evidence equally likely, we can factor out the likelihoods and take that 1/2 term out of the equation. This reduces to counting the relative prior probability of Omid being upset with you over the other prior probabilities, which yields intuitively 4 out of 100. That is, we have a 4% chance that Omid was upset with you, given that face. Here, because of the equal likelihoods, the posterior probabilities are the same as the prior probabilities, indicating that the face that Omid made is not particularly strong evidence for anything. That said, you could plug in different numbers for the likelihoods that you find more plausible and see what they would yield. Our moral here is that merely recognizing the existence of alternative hypotheses and the fact that we must distribute our credences over all of them can give us a better idea of how confident we should be in our first hypothesis. Typically, this process will make us less confident than before we did it, but more accurate. Let's move on to our next corrective for confirmation bias. In science, it is often said that we try to falsify our hypotheses. We can use probabilistic reasoning to make this more precise. We aim to find predictions that we derive from our theory, so that the probability of those predictions conditional on our theory is quite high, but that are themselves unlikely, such that their marginal probability is quite low. Tests of such predictions are the most likely to show that our theory is false, such that the probability of our theory conditional on that failed prediction is low. This is not the same thing as strict deductive falsification, which, on careful examination, does not really happen in science. However, it is a probabilistic analog of the sorts of conditions under which we can get substantial evidence of the sort that would change our minds. That is to say, of the sorts of learning situations or experiments that we expect to be the most informative. Let's work through how this would be so. Let theory H predict event E, such the probability of E given H is high, so the probability of not E given H is correspondingly low. But E is unlikely. The marginal probability of E is low, so the probability of not E is high. Imagine that the prediction turns out to be false, so that not E is true. Consider Bayes' rule. The probability of H given not E can be written in terms of the product of the prior probability of H and the ratio of the marginal probability of not E, under the likelihood of not E given H. So now what we have is that whatever our prior on the hypothesis, we know that the greatest decrease in the probability of H is produced just when the likelihood of not E given H over the marginal probability of not E is smallest. That is to say, when the probability of not E is very high, and the probability of not E given H is very low. we saw that when a theory H strongly predicts an event E, and E is on its own unlikely to be true, then when E turns out to be false, it provides strongly disconfirming evidence against the hypothesis or theory H. This is the case of a strongly informative outcome that is correspondingly quite valuable. Now imagine that E does not turn out to be false, but rather it turns out to be true. The prediction of the theory is borne out. Consider again what Bayes' rule tells us. Now, the prior probability of the hypothesis or theory H is multiplied by the ratio of the probability of E given H over the probability of E. Recall that the probability of E was very low by stipulation. And the probability of E given H was very high because H predicted E. Here we see that the greatest increase in the probability of H produced just when this ratio is largest. So what we have found in this case of a prediction that is very unlikely to be true, but for a theory which makes it very likely to be true, that is to say, strongly predicts it, this set of conditions presents the highest expected value in learning. Because if the prediction turns out to be false, we change our belief quite strongly. And if the prediction turns out to be true, we also change our belief quite substantially. Let's consider an example. The historical episode of the prediction of the deflection of starlight by general relativity. General relativity predicts that due to the warping of spacetime, light waves will be deflected when they pass near massive bodies, such as the Sun. In 1929, this was tested with photographs during an eclipse. The prediction of the theory was that starlight, just grazing the Sun's surface, should be deflected at an angle of 1.75 arcseconds. Let's represent this learning situation probabilistically. Let H be the proposition that general relativity is true. E be the observation of starlight grazing the Sun at the precise angle of deflection of 1.75 arcseconds. This value was predicted by the theory, so the probability of the evidence or observation given H was high. This specific deflection, 1.75 arcseconds, was highly unlikely otherwise. So the marginal probability of E was very low. Hence, this was strong evidence for general relativity. And the posterior probability on the theory, on observing the successful prediction, should have received a substantial boost from the ratio of the likelihood of the evidence given the theory over the marginal, unconditional likelihood of that evidence. What we see here is a vindication in probabilistic terms of the value of looking for disconfirming evidence. The rationale, it turns out, is that disconfirming evidence is a case of an opportunity for high value in learning. Let's turn to base rate neglect. Base rate neglect is a tendency when presented with relevant base rate information, for example, general information on the prevalence of an event, and specific information, that is, information pertaining only to a specific case, to ignore the base rate or undervalue it in favor of the individuating or specific information, rather than optimally integrating the two parts of our information. A straightforward example of base rate neglect comes from the Harvard medical tests and a number of studies since, which roughly presented medical students and doctors with the following information. A routine medical exam produces a positive test result on a 90% accurate test with a prevalence of 10%. And by 90% accurate test, we mean, for simplicity, both the sensitivity and the specificity were 90%. That is, both the probability on having the disease of getting a positive result was 90%, and the probability on not having a disease of getting a negative result was 90%. Medical students and others respond that it's 90% likely that this patient has a disease. Right? The correct answer in this sort of case is actually 50% when one factors in the base rate. This is base rate neglect. The corrective in such cases is sometimes called taking the outside view. That is, not just thinking about how likely our evidence is given our hypothesis, but also about our prior probabilities on our hypothesis. In the medical diagnosis example, the likelihood of a positive result given a disease is quite high because we have a 90% accurate test. However, the disease is fairly rare. Our base rate, which informs our prior. These two need to be combined appropriately in the way described by Bayes' rule. Very often, the base rate or prevalence of an event is the best initial forecast for that event. For example, I'm considering the hypothesis as to whether I will finish the project on time. The planning fallacy often makes it so that folks are overly optimistic about their capacity to finish the most recent project on time. To correct this, we might start with the base rate. How often have you finished similar projects on time? That will give you your prior. Typically, this is less rosy than one's current intuitive anticipation for how long it'll take to finish this project. Consider the hypothesis stock X will close up at the end of the day. One place to start in predicting the probability of this proposition is, in the past year, how often has stock X closed up at the end of the day? Consider the hypothesis the incumbent will win re-election. Once again, a good initial prediction is, for example, in the past years, how often have incumbents won re-election? Determining the right prior is important but challenging. Consider the proposition that the incumbent will win the election. In the past 50 years, how often have incumbents won re-election? This is to be our prior. Well, which sort of incumbents? Representatives, senators, presidents? This is a bit easier if you know the kind of incumbent you're thinking about. But what sort of time frame? In the past 5 years, 10 years, 20 years, or 50 years? This is a bit harder. You have to make estimates about the balance between how relevant different distances in time are. Surely last year is informative of this year when it comes to political elections, in most cases. However, what about longer periods? That has to be balanced with still getting information in order to make a more accurate prediction. If you make it too specific, right, only in the last 6 months, you might not have enough data to inform a reasonable prior. What regions? Local, regional, national, international? Some of these are going to be more or less relevant. Where do you draw the line as to what data to include in your reference class to make your estimates for the base rate? A more specific prior typically means less but more relevant data. This is a basic but unavoidable trade-off. While it seems like there might not be any objective answer, it is a fact that better forecasters get better at figuring out how to do just this. This is a skill that can be developed. For the last bias that we will consider, we look at the conjunction fallacy. The conjunction fallacy occurs when one attributes greater plausibility to a more complex proposition than to a simpler one, when the more complex proposition cannot have greater plausibility. Note that this typically occurs because of coherence bias. When we feel that stories with more interconnections are more plausible than ones with fewer interconnections, without regard for the logical structure of those stories. The famous example of this is known as the Linder problem or Linder paradox. Subjects in an experiment were presented with the following vignette. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which hypothesis is more probable? Linda is a bank teller, or Linda is a bank teller and is active in the feminist movement? The answer is that the hypothesis that Linda is a bank teller cannot, as a matter of logic, be less probable than the more complex hypothesis that Linda is a bank teller and active in the feminist movement. Many participants get this wrong. Let's visualize the probabilistic reasoning involved here. The set of folk who are bank tellers is going to strictly contain the set of folks who are bank tellers and also feminists. Hence, the probability of being a bank teller and feminist can never be greater than being a bank teller, and indeed will almost surely be less than the probability of just being a bank teller. This is captured by the proposition that for any statement P, conjoining it to another produces a proposition, a conjunction, that is at most as probable as P. The deeper point behind this simple example is the admonition to beware of the logical complexity of propositions as this affects their probability. If you hear a story hypothesis argument composed of and, you should not be thinking, this story is so coherent, look at all of its interconnections. Rather, you should be thinking that the probability that at least one of the key statements involved is false is increasing with each conjunction. Let's think about the general relationship of logical structure to probability assignments. At the very bottom, one can consider the probability of the contradiction, that nothing happens. This is always equal to 0. Going up from here, the least probable propositions are those that are composed of many conjunctions. So for example, the probability of P and Q and R is weakly less than the probability of P and Q, which is weakly less than the probability of P. Continuing upward, the probability of propositions increases as one introduces disjunctions, a broader set of possible worlds in which they might be true. So the probability of P is weakly less than the probability of P or Q, which is weakly less than the probability of P or Q or R. And ultimately, the probability of the tautology of anything happens is at the top of the hierarchy, at 1. It can be helpful to attend to the logical structure and complexity of hypotheses. because there is a tension between what makes a story believable for us and what makes it objectively more probable. Punditry is typically optimized for coherence and believability rather than for probability and for prediction. Pundits, like those tested in the projects under the expert political judgment umbrella, are characteristically good at telling believable stories and characteristically bad at actually predicting anything. They are leveraging this bias. Let's take stock and step back to think of a few helpful principles for thinking about when to trust judgment. After decades of research, we do actually have some compelling characterizations of the conditions under which we should trust judgment. Our own, experts, what have you. The two conditions can be interrogated by asking the following questions. Is the thing predicted sufficiently regular, structured, and the feedback received sufficiently clear so that the forecaster has a chance of actually getting good at predicting it? Further, has the forecaster had enough experience under those conditions of regular and clear feedback to actually learn from those conditions? If either of these two fails, if the forecaster's learning situation is too irregular, their feedback too ambiguous, or their experience too little, we should not expect their judgment to be reliable. In developing your forecasting skills, you might be interested to know which traits best predict good prediction. There are several that stand out. The first of which is pattern recognition. This is a ubiquitous and often informative measure that one can attempt to infer through tests like the Raven's matrices shown here. Another trait that predicts good prediction is known as actively open-minded thinking. For example, folks who agree with the following: people should take into consideration evidence that goes against their beliefs or opinions, tend to be higher in this trait. Whereas people who tend to agree with the following proposition, one should disregard evidence that conflicts with one's established beliefs or opinions, tend to be lower in this trait. This is indeed a disposition that can be cultivated. The third key trait that predicts prediction is known as cognitively reflective thinking. This is, in a sense, how much one is disposed to employ type 2 or reflective reasoning. This sort of question attempts to get at this trait. If a cell phone and a pair of headphones cost $450, and a cell phone costs $400 more than the headphones, how much do the headphones cost? Typically, when folk look at this sort of a problem, they'll jump to $50 as the answer. However, pausing and thinking through the problem and past one's initial gut response will deliver one to the correct answer, $25. Cognitively reflective thinking, too, can be cultivated and consists importantly in not stopping at gut reactions, but rather pausing, making our understandings explicit, and interrogating them. It has also been repeatedly demonstrated that probabilistic reasoning is an important predictor of good prediction. That said, not just theory, but practice is essential. And it appears that as forecasters go on, practice becomes more and more important and predictive of their performance. In terms of getting at the highest levels of prediction, what has been found is that super forecasters, or the top performing fraction of forecasters in tournaments, are some of the best at anticipating the outcomes of real world events. But they too can be improved with training. Further, combining these super forecasters into collaborative teams can improve their performance still. And then aggregating the results of those teams using algorithms produces the best performance of all. For those of you interested in places to hone your prediction skills, I encourage you to sign up for one of these prediction markets, where you can get that essential element of practice. For further reading, I recommend Yudkowsky's Sequences, Rationality from AI to Zombies, Tetlock and Gardner's Super Forecasting, and Kahneman's Thinking Fast and Slow. To recap, there are a host of compelling reasons to think in probabilistic terms, and a number of techniques to begin doing so. Behind it all is the logic of Bayesian inference, which tells us how to change our minds in light of new evidence, and how to combine what we knew before with what we have just learned to produce our newest optimal predictive probability estimates. In all this, we should think like a forecaster. That is, we should keep with us the lessons of the fox, to be humble and grapple with the complexities of the world, taking a little bit from many perspectives. Critically, we should get feedback and track, keeping a record of our predictions and making them clear enough to detect when we're wrong. Importantly, we should correct for our biases. For base rate neglect, we need to find the correct reference class, balancing the inside and outside views. For confirmation bias, we need to think of alternative hypotheses, fleshing out the space of possibilities, and looking for disconfirming evidence, which is where the most, in expectation, valuable learning occurs. And finally, the conjunction fallacy, for which we can correct by recognizing the logical structure of claims and its effect on their probability, and resisting the tendency to think that storytelling and highly interconnected and complex hypotheses are more likely. As we look at many complex theoretical and empirical topics in the space of AI, safety, and existential risk, having these skills and attitudes will be better for us in expectation than not having them. That said, predicting advances in artificial intelligence may be particularly difficult. This is because we have not experienced this before. So determining reasonable reference classes to anchor prediction is quite non-trivial. And also because, as we will see, we may not have many chances for trial and error learning. We may have to get this right the very first time. Good thinking, and take care.